speed of light is invariant. The results of these experiments are invariant. But invariant for what observers?
Wait, slow down. What's invariant again?
So
Doesn't change.
yes.
Non-invariant.
They're invariant between transformations between inertial reference frames. So here is an image where you have OD chasing Garfield, and they are running at different velocities. So now if OD were to perform a series of experiments while running somehow miraculously, like he were to drop a ball or he were to do any sort of experiments to check if Newton's laws applied, and if Garfield would do the same experiments, they would have no way of determining any difference between these two experiments. And that's what we mean by invariant. They're invariant between if we change which reference frame we're looking at. If we look from Odie's perspective versus if we look from Garfield's perspective versus if we look from, what's the guy? His name Jim?
John.
John.
I think so.
If we look from John, who is just standing in his perspective, they're all going to be the same. Okay. Yeah. So in inertial frames, if we were to formally define them, objects remain at rest or travel at constant velocity in absence of outside force. So what's another way to think of that? What's that called? Newton's first law applies. So, yeah, as we said earlier, special relativity is special because all of our results are calculated from inertial frames. So what is an example of a non-inertial frame? Yeah, an accelerating rocket, or, because we're more boring, an accelerating car. Very exciting. So here in the car we have a pendulum. So the force is applying in that direction. So the car is going to accelerate forward. What happens to the pendulum then if the car is accelerating forward?
It moves backward.
It moves backward. And why is that? Because the force doesn't travel instantaneously, right? So the force is applying at the top, and the ball, on the other hand, is still moving at the constant velocity forward that it was moving at before. So it swings backward. And that's from the perspective of someone that was standing by the car on the outside. So if I am an inertial frame, and I'm not accelerating, I'm watching this happen, what I say is that, oh, the force that was applying to move the car to accelerate it forward, it doesn't reach the end of the ball, so the ball swings backward.
Wouldn't the ball just like remain like traveling at constant velocity? It shouldn't move backward relative to observer that's standing on the ground, right?
True. Okay, relative to the observer moving on the ground, it still moves forward, but it doesn't move forward as far as the car moves forward. So if you were to look within the car, the ball is backward, but it's still forward relative to the observer, if that makes any sense.
No.
That doesn't make sense? Okay.
From my perspective, the ball's still going to move left relative to the car.
Yeah. No, so you're standing here. The car is moving forward, and the ball is still moving forward at constant velocity. So it's moving forward, but it's not moving forward as quickly as the car.
Okay.
So it's going to move backward within the car.
Which the car's already moving.
Yeah.
Oh.
It's just accelerating faster.
And if I'm in the car, it also appears to swing backwards.
Yeah, so now we're going to look at what happens if you look at, you're the perspective of within the car. So is the car an inertial frame? No. So here we'll notice there are some issues, right? So we have the pendulum swinging frame. Okay, does Newton's second law hold from the car's perspective? What is Newton's second law? F net equals ma, right? Yeah. So, okay, so what are the forces that are on this pendulum? Yeah, so tension, right? And gravity. Okay. And so material origin for it. Like, we don't see anyone hitting the pendulum, and we don't see a charge that is, pulling the pendulum back. There's no material origin. Or we call it the spooky force. There are a lot of different words. Spooky force, fictitious force. No. Pushing it backwards. Okay, so when a car turns, which way would you lean within the car? Yes. Wait, did I use that right? Wait, sorry.
Sorry, can you go back just one slide to the spooky force?
Yes.
So we would not see a spooky force if we're the outside observer?
Yeah, because from the outside, it's perfectly logical that it moves back. Because
What's
you see
the
that
force
the car is accelerating.
So the car is providing some force that direction?
It's not that the car is providing force, it's that the car, you see that the ball is moving at constant velocity, whereas the car is accelerating.
Okay.
So the
okay.
ball is going to
Okay.
fall backwards.
Okay. So
But if
it's just taking time for it.
It's just taking time.
Okay.
But if you're in the perspective of the car, you would say that, no, I'm not accelerating.
Yep.
Everyone else is accelerating. So there has to be some explanation for the ball's movement. And that's where we assign this spooky force. Yeah. So the same thing applies for, this is, when you're changing direction, because changing direction is accelerating, right? So, yeah, if you're swinging to the right, if you're turning to the left, you're going to move to the right. So, yeah, so the spooky force in there is going to be in the exact opposite direction of the real force. So the real force would be the force that is causing the car to turn, or the force that is causing the car to accelerate forward. So, and in both cases, because it cancels out the real force, it has to be proportional to mass. And so the other reason, like, the other thing you can think about is, let's say you're in the frame of reference of someone like, of the car itself. So from your perspective, there is the real force, but then there's also the spooky force canceling it out. So that's why, from your perspective, you're like, I'm not accelerating, the two are canceling each other out. But if you're the pendulum within it, you're just experiencing the spooky force, you're swinging backwards.
What's the real force on the pendulum? Like if you're standing from the outside?
So from the outside, there is no real force on the pendulum.
Okay.
So the reason why the pendulum swings backward is just because of the velocity is slower than what the car is accelerating to.
And if you're inside the car?
If you're inside the car, you don't think you're accelerating, so you come up with the spooky force as the explanation for why the pendulum swings backward.
Then where is the real force coming?
The real force is what's causing the car to accelerate. It's what makes the frame of reference non-inertial.
Okay.
So it's actually pretty powerful, the fact that the spooky force has to be dependent on mass. So look at the forces you guys have written down, and what forces do you guys have? You can just call them out.
Gravity.
Gravity, right?
Strong force.
Yeah. Here. Yeah. So out of these forces, which ones are dependent on mass? Or rather, which one? Just gravity, right? Which is sort of interesting. Which one is proportional mass? Gravity, yes. And also the spooky force. So now we're going to make a sort of jump here. We're going to say that what if gravity could be thought of as a spooky force in a certain frame? So it could be interpreted as a spooky force as we accelerate. Okay, so here,
Wait, slow down, I gotta think about that question.
but I have a hypothetical example that will hopefully help you think of it. Okay, so we have two scenarios. These are two very fancy looking elevators here. So one elevator is at rest on Earth. I don't really know what that lady is, who she is. But anyways, she's there. She's in this, this elevator. And it is at rest on Earth. So she's feeling a force, right? What is that force? And then there's another frame in which this lady is in an elevator accelerating in space. So here, in the frame, she is in the frame of reference of the elevator, right? In space. So she's in this non-inertial frame of reference. So what we said earlier about spooky forces is that it will exactly be in the opposite direction of the real force. So the real force is pointing upwards, right? So what's the force that the lady in space is going to feel? What direction is it going to be? Downward, So she'll feel that in both cases. Is there any way she could determine, without like looking outside the window or something like that, whether she's in space or on Earth, whether it's gravitational force she's feeling or a spooky force from acceleration? Can you come up with a scenario?
Need to make an experiment, yes.
I mean, if you can come up with a way to determine these, then that would be very impressive, because I don't think anyone has yet. So the fact that these two scenarios, that the force of gravity that she would feel and the spooky force as a result of the acceleration that she would feel, the fact that they are indistinguishable is the weak. Oh wait. I want to go through this one first. Okay, so, and the formal statement of it is, suppose that the free fall acceleration under a certain gravitational field is g, then locally it is impossible to distinguish between the motion of particles in this gravitational field and in an elevator accelerating at g relative to a global inertia frame. So the reason why we have to say locally, does anyone have a guess? Does gravity change based on where you're located? Yes. So like the way that this person, the lady in the lady in the elevator could tell is that she would simply measure the force she's feeling at different times when she's on. No, I guess that doesn't. Wait, sorry, that would be more relevant for this one. But if she's changing her location, where she is in respect to gravitational field, she would be able to tell. But locally, in this one spot where the gravitational field is constant, she can't tell as long as it's the same amount that she's accelerating by upwards. So there's another example of this is, let's say that that instead the elevator is in free fall or it's stationary in space. So when the elevator is in free fall, does she feel any forces? Like what does it mean to feel gravity?
Like the ground pushing up against you.
Yeah, so if you're in free fall, you're not really feeling the ground pushing up against you. You're not really feeling anything. And the same goes for if you're in space and you're stationary. You're not really feeling anything. So, wait, Darius, correct me if I'm wrong, but when they're simulating gravity at times, they do that by having an acceleration, right?
Yes.
Yeah, so if scientists want to do an experiment that's, where they have the presence of gravity, they would do that by creating an accelerated frame, because there really is no difference.
If you ever been to the amusement park where the Gravitron, where it spins around really fast, that kind of, they talk about that in terms of g forces. Accelerations are often termed in terms of g's, and that's kind of the start of the reason why.
So, there are lots of cool consequences of this, as you might expect,
Spoilers.
and Eric is going to talk about them.
But
Oh,
before Eric talks
Eric
about them,
Robbins.
yes, you can say it. Yeah.
I'm done.
Tell them to work on.
Hello.
Yeah,
Oh.
it's your part. Yeah.
Homework.
Yes, you guys should work on question 1.
Wait.
Question, no, but question 1 in part 2.
No, you guys should work on part 2 and part 3.
Part 2.
Right. So it's paradoxical and Doppler shift. So the paradoxical thing is more qualitative, and then the Doppler shift question is and if you want more pizza, then we'll paradoxical.